Okay, it's time to begin. So first of all, just a reminder, again, this is a reminder, it hasn't changed. It's the same date that's in the syllabus and also on Canvas. And that's 2 weeks from today. That's the day of the midterm. That's Thursday, May 11th. So on every table, I put enough copies for each person. There's a handout that has my midterm policy and also topics for the midterm. So just wanted to give you that this week. It's not a test that you want to wait until the night before to start looking at. So wanted to give you that information plenty of time before the test. And, look it over. And then next week, if you have any questions, just ask me then. Okay. Also on the table, there's another handout that has 4 copies, 1 for each person. And that has information about a 7-segment display on your basis board that we're going to talk about today. And also on the flip side, it has a portion of what your constraints file is going to have to look like for lab 3. Because lab 3 does include a 7-segment display. And there's one other handout, the handout with the diagram of the CPU or the microprocessor for CPE133. And I just put one on each table because not everyone needs a copy of that. If you wanted your own copy, I can get you one, but we're going to be referring to that just briefly during today's lecture. So today is about decoders. And after today, you'll be able to complete lab 3. Also, I want to start off talking about BCD, a binary coded decimal. This is something that often comes up with 7-segment displays, and I'll discuss why that's so later on. But where I want to start is with something we've already done. In that first class, when we were talking about number bases and number base conversion, remember we did hex to binary, binary to hex. And do you remember how you can convert between these 2 bases without going through base 10? Like going directly from hex to binary? Right. Each hex character can be represented by a group of 4 binary bits. All right. Remember that has to do with the relationship between 2 and 16, right? That you can raise 2 to the 4th power, get 16. So that's why it's 4 bits. So I can write each one of these hex characters as a 4-bit binary group. So what would 9 be in binary? 4-bit. 1001. 1001. How about 5 and 4-bit binary? 01. How about 4? 01. 0100. How about 1? Right. We don't have to include the lead zeros, right? Because we're going to change it. So when we do this technique here, we're actually doing base conversion, right? That this in base 16 is equal to that in base 2. And back when we first did this, and I don't know if anyone took me up on my suggestion, but I said at the time, I said, well, if you want to prove it to yourself, this actually works. Take this base 16 number, convert it to base 10, take this base 2 number, convert it to base 10, you're going to get the same number. It's going to be the same base 10 number. Okay? Okay, well, the reason I started out with this is because when you go from BCD to decimal or decimal to BCD, it looks the same, even though it really isn't. Okay? So the first thing is BCD, which again stands for binary coded decimal. It's a subset of binary. Okay, it's a 4-bit binary from 0 to 9. Okay, so in BCD we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. So 10, 2, 4, 6, 8. Right. You see, I'm just counting a binary. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is all the 4-bit groups you have in BCD, because again, it's just a subset of binary. So now, if I have this 1459 in base 10, and I want to show it as BCD, I just write each decimal, right, each digit as a 4-bit binary BCD. So you see this 9 would be 1001, this 5 would be 0101, this 4 would be 0100, and this 1 would be 001. And you see this is BCD. So we would put subscript BCD. So even though this BCD looks just like when we did this conversion from base 16 to base 2, we are not converting bases here. This is not conversion, right? Because again, the reason why 16, right, base 16 to base 2 conversion works by doing this grouping of 4 is because of this relationship, right? 2 to the 4 is not 10. So when you write each digit, right, each base 10 character as a 4-bit binary group, you're not doing base conversion. Okay, I mean, the reason this is done is because of something called a 7-segment decoder that we're going to get to later. Okay, but the main point I want to stress is that we're not doing base conversion. Okay, we're just representing this base 10 number in this other form called BCD because it fits into a certain kind of decoder that we're going to talk about. Okay. All right. So we good? All right. So let's go ahead now and talk about decoders. And we're going to start off with the definition of a decoder. A decoder is a device that converts digital signals from one form to another form. And I'll give you examples of each here. I mean, it's a very broad definition. You know, just about every circuit does this. Every digital circuit does this.
I have a question about BCD.
Okay.
These rows,
In BCD, you do have to include them. Okay, yeah, when we do base conversion, you don't, because see again, when you do base conversion, this has numerical value. Okay, when you're doing BCD, it's still representing this number, but in of itself, it doesn't really have numerical value. It's not like binary. So, again, I think this will make a little bit more sense once we get further along here. Okay. Okay, but anyway, getting back to this, this is a definition of a decoder. And like I said, it's a very broad definition, and there are many kinds of decoders. I mean, there's just 1,800 kinds of decoders. Okay. But one example of a decoder is on that diagram, okay, the CPE133 microprocessor diagram. There's this module labeled CU. Did I get that right? Is it CUGCR? Yeah. This stands for control unit decoder. And what this decoder does is that it takes an instruction and it converts it into mux select bits. See, if you take a look at that diagram and the control unit decoder is up in the right-hand corner. It's CU, DC, DR. And if you look on the left side, that's where the inputs are. You'll see IR, and then inside brackets, you see 14:12. Also, you'll see IR with a 30 in brackets. And then if you look up a little bit, there's another input where it says IR and then 6:0. Well, IR stands for instruction register. And again, we're going to talk about registers later on this quarter, but right now, the reason I bring this up is what this decoder is doing is it's taking certain bits from an instruction. And you'll learn in CPE133 that this microprocessor has 32-bit instructions. Each instruction is 32 bits. So 14 to 12, that's 3 of the 32 bits that's going into an input of this decoder. And 30, that's the 30th bit, so just a single bit. And then 6 to 0, those are 7 bits. Bits 6 through 0. So these bits that come from the instruction go into the decoder and it converts it into outputs, these 5 outputs. And you can see here that the output ALU fun is 4 bits, ALU source A is 1 bit, ALU source B is 2 bits, PC source is 3 bits, and RFWR SEL is 2 bits. Well, those outputs of the decoder, look at where they go. If you look at the other part of the diagram, you'll see that ALU fun goes to this ALU, and when you take that class, you'll learn that the ALU is just a big mux that can do mathematical and logical operations. So that ALU fun is a select input to a mux. ALU source B is also connected to a select input of a mux. ALU source A also goes to the select line of a mux. PC source goes to another select input of a mux, and also the RFWR SEL goes to a mux. So you see this decoder, it's taking in an instruction and it's outputting these bits that control the muxes, right? Because we learned how muxes work last week, right? That the select input of a mux determines which input connects to the output. So you see by outputting these mux select bits, that decoder is controlling how the data flows through the microprocessor. All right, so it's taking the instructions and then it determines the data path through the microprocessor. Okay, so I just bring this up as one example of a decoder. Okay, like I said, there's many examples, but this is one that you'll see and learn more about in CPE133. In this class, what we're going to focus on and what's part of lab 3 is a 7-segment decoder. Okay, and you'll see what the use of it is as we go along here. Okay, but any questions up to this point?
So the decoder, like version like the simple one, it can be made just the stuff that we already know, right? Like it really just be like the regular inputs and outputs of a module. Like it could take in 3 things and it could output 6 depending on the inside.
Yeah, I mean just about anything's a decoder.
Yeah, okay.
Yeah, because just about any digital logic circuit is going to take some bits, and convert it to some other, well, take some bits that represent some sort of signal, and convert it into something else. So yeah, but there are specific, or there are some very common types of decoders, and a 7-segment decoder is one of them. Yeah. Okay, so this is lab 3. We took a look at this last time. We're going to talk about it in a little bit more detail today. But again, I just want to point out that lab 3, it has an RCA, okay, the same one that you designed for lab 2. It's got this 2-to-1 mux. How many people were able to build and test their 2-to-1 mux and it worked? Had a successful simulation? Oh, not that many. Oh, I had more people in my 8 to 11, it was like about half the class. Okay, well, that's where almost everybody is going to have to start today is with the mux. You want to do that one first, using an if statement like we talked about last time. Okay, and then what's new today is this decoder. Now, in the lab 3 diagram in the instructions, it has this input of the decoder as BCD, okay, the binary coded decimal. I'm changing it to hex, so I want you to do the same thing. Okay, so instead of calling this input BCD, we're going to call it hex. And I'm going to explain why I made the change coming up. Okay, it's just going to make this decoder a little bit more interesting. Okay. Now. Remember, you saw this before. You saw this type of notation when we talked about the ripple carry adder that was made out of adders. Okay, remember I had the dash box, and like inside we had the adders, right? The 1/2 adder and the 3 full adders. And that diagram was showing that the RCA, the overall, was made up of those adding circuits. Well, same sort of thing here. See, the lab 3 design is made up of these 3 modules. And just like you used a structural model to connect all the lower level components, the adders of the RCA together, well, you're going to use a structural model to connect these lower level modules together, okay, to get our lab 3 design. And then remember, your inputs and outputs that are outside the dash box, those are your main inputs and those are your main outputs, right? Going into your overall design. And that's what the high level black box diagram shows, right? Remember this high level black box diagram, it shows your main inputs and your main outputs. So, you could call this, 7 seg lab or whatever you want to call it. Or call it something other than lab 3, be a little bit more descriptive. Okay, so what are we going to put on the input side of this high level black box diagram that represents this overall circuit? What are we going to put? A and B, right? Because A and B are our main inputs. Those are the 2 binary numbers coming in that's going to get added by the RCA. B. Okay, what are our main outputs? Right. The 7-bit output called seg and this 4-bit output AN. So that's what goes. And okay, so when you go to design your overall structural model that ties all these lower level modules together, in Vivado, that's what you're going to have for inputs to your overall is these 2 inputs, and these 2 outputs are going to be your overall outputs. Okay. Now we're going to come back to this diagram after we talk about how a 7-segment display works. We're going to come back to this diagram and I'm going to explain, what's going on, like why we have this particular data going into the mux. And notice that the select input of this mux is connected to the carry out of the RCA. Okay, so we'll talk about why things are connected the way they are. Okay, but before we do that, let's talk about what a 7-segment display is. You've probably noticed that on the basis 3 board, when you're looking at the board with the switches on the bottom, over towards the left, there's these 4 displays. Okay, and those are the 7-segment displays. And if you take a look at each one of them, there's 4 individual ones that are all close together, part of the same component, actually. What you would see is that the segments, which are LEDs, okay, light emitting diodes, they're oriented as a figure 8. And a 7-segment display, it has a pin that's often labeled AN. And it also has pins that, as you can see here, are labeled with letters A through G. And the convention, and this is something that I've always seen the same. I haven't seen anything different than this when it comes to 7-segment displays. So I think it's pretty much universal. That the top segment is the A segment. The B segment. The C. This is the D. Now, that's the G segment. Okay. And inside that 7-segment display, the circuit like this. Now, again, you're not going to get tested about any circuits in electronics. I'm going to mention a little bit about circuits and a little bit about electronics here just to hopefully get some understanding of how this 7-segment display works. Now, are there any people in the audience that knows what a diode is? No, no problem. If you know what a diode is, you probably can guess what it's in short. Can you guess what that is? The one side of the diode is called the that AN stands for human. fact, this is called. Hand side of the diode. An LED is just a diode that can emit light under the right conditions. And this is a diode circuit symbol. In the arrow, that's the input side. Okay. And you see it's called common anode because all the anodes of all the LEDs are all connected together. Okay, they're all connected to the same connection, or in circuits we call a connection a node. Okay, so this is all the same node. The other side of the diode, therefore the other side of the LED, is called the cathode. Okay, so all these segments, okay, segment is an LED. Well, all the segments are all connected together on the anode side, but they're not connected together on the cathode side. They're separate on the cathode side. Okay, and then also there's this inverter that's between the anode pin, this AN pin, and where the common anode is. Now, the other thing is, in order to get current to flow through something, you need to have a difference in voltage. And it's the current that flows through a diode that makes it light. And if you don't have any current through an LED, it's not going to light. Okay. So, in order to have any chance in one. Something I mentioned a few weeks ago. 0 to 1 they represent voltage levels. 0 to 1 represents some plus amount of voltage, usually 5 volts or 3.3 volts. 0 represents 0 volts. We often call 0 volt ground. So, because we have this inverter, if I want a 1 on this output side of the inverter where the common anode is, what do I want on the input side of the inverter? Okay, so I have a 0 here at the anode in order to put 1 on this common node where all the anodes of the LEDs are. Okay, so now in order to light an LED, you have to have a voltage difference. So on the other side, the cathode side, to get an LED to light, to get one of those segments to light, I would need to have a 0. 5 volts or 3.3 volts across the LED to current flow through C light. Okay. If you don't want a segment to light, right, so no light, you put a 1 on the cathode, because if I have a 1 on both sides, that's the same voltage on both sides. It means it's a 0 volt difference. If you don't have a voltage difference across something, current has no chance to flow. Okay. In order for current to flow, you get a voltage difference. Okay. Now, another thing is, and this is something particular to diodes. Diodes will only allow current to flow in the arrow direction when the voltage on the anode side is greater than the voltage on the cathode side. So if you were to reverse this, if you were to put a 0 on the anode side and a 1 on the cathode side, even though that's a voltage difference, a diode wouldn't allow current to flow and the LED would be on. Okay? So anyway, a little bit of circuit. Key thing here, as far as we're concerned in this class, is that this bit here, this bit here, the AM bit that determines what this common anode voltage is going to be. This controls if you don't have a 0 and values are, the display is not going to light it up. The segments are always going to be off, no matter what the cathode is doing. So controlling whether the display will light it up. These bits over here. These control segments. If I have the 0 on the Sec5, the 0 is provided by 80 also the light. So whatever it's 0, whatever it's 0, it's on that signal, on that signal. You see, that's what it's. RCA. We're going to make the appropriate choices to show the characters that we want to be shown. Now, and as I'm turning the camera, are there any questions up to this point before we look at the truth table? Not too much circuits for you, people that haven't had circuits. Again, you're not going to be tested on the circuits. They're already found. Definitely all makes sense. Okay, let's go ahead and look at the truth table. We're going to come up with a hex, the 7-segment decoder truth table. So this hex, that's the binary of this input that's coming from the output of the RCA. Okay, coming from the sum output of the RCA. So let's start with, well, actually, before I put this on here, what it's going to write on the board. How many characters does text have again? Hexadecimal has how many characters? Yeah, 16. So that's why I have 16 rows. We need a row for each hex character. So we'll start with the hex 0. And we want a hex 0 when this 4-bit binary is all 0. Like this hex and binary is 4 zeros. Right, so next to the hex character, I'm putting the 4-bit binary that goes with it. Okay, so when we have a 0 coming from the RSA right into our decoder, what we want to show on the 7-segment display, we want to show a 0. Right, so that means on our 7-segment display, we would have to light the A, B, C, D, E, F segment. Right? We don't want the G segment for that. Right? So then we have a 0 showing up on our 7-segment display. Okay, so what are we going to want these cathodes? See, these are the cathodes. They're the Seg cathodes. So what do we want these bits to be? To make a 0 show up on the 7-segment display. In other words, which ones do we want to be 0s and which ones do we want to be 1? Only D segment would get a 1 because that's the only segment we want off. We want all the other segments on. So you see, we want the G cathode to be a 1, and we want all these to be 0. You see, when you design this decoder, you're going to design it such that when there's 4 zeros coming in, right, the binary 4 zeros, which is a 0 hex, you're going to make these 7 bits such that it's going to light up a 0 on the 7-segment display. Well, I guess the only reason I do that is because I call this like the 0 bit, and this one was the 6th bit. I suppose you could do it the other way. I don't know if it's really standard. I mean, most of the time when I see a decoder like this, it's usually done like this, where they call A like the least significant. But there's no, you could do it the other way as the decoder. Okay, the next thing is we're not representing this. This is just for bookkeeping. Okay, well, yeah, bookkeeping and also just for when you go to test this in Vivado, having these 7 bits of the Seg cathodes, having it in X can make it a little easier when you're checking to make sure that you're designing. So how would I write 1 0 0 0 0 0 0 in binary? How would I write that as a X? You're gonna group the bits in one. You're gonna group four, starting with those anything else. So you got two groups here.
0.
Yeah, right here. Yeah. Everybody see that? This would be 40 pets. Right, this is 4 here. Okay. Now, the activity today, you need to finish this page. Ready? 16 rows. You're gonna go 0, 1, 2, 3, 4, all the way to one row. You want to see another row? See which row do you want to see? Which one? Something that's interesting. So D would be here, right? You see an issue that capital D. Well, first of all, let me say that usually when you see hex, most often when you see hex, the letters are in uppercase. Now, again, there are some CPE 233 professors I know that they use lowercase. Okay, so it's not like a, you know, not written in stone anywhere. Okay, but most of the time in this lab, okay, for this lab, and also for this course, I would appreciate it. Well, for this lab, you have to use uppercase letters when possible. And then outside of this lab, I would prefer that you use uppercase. Okay. But you see, we run into a problem using an uppercase D. What's the problem? Yeah, it's going to look just like a 0. So, you know, that has to do with the limitation of this display. There's only 7 segments. You know, they have displays that have more segments. You know, they have displays that have 16 segments, 32 segments, you know, so you can do a lot more characters with it. But this is a 7-segment display, so we're limited. So because we can't do a capital D, it'll look like a 0. We're going to use a small case D, right? So, you know, a D like this. And what binary 4 bits is D? The D and X is what? 4-bit binary. One, 0, 1. And it's a small case D, so we'll want, let's see, we'll want B segmented, D segmented, G segmented, D, and E, right? To make it a small case D. So to make a small case D, you want everything like this, A and F. Everybody agree? So what are our 7 bits gonna equal if we just want B, C, D, E, and G? We don't want A and F. Where we got one thing. C, E, 0, A. Let's go check for sure. If you see a mistake, A, 1. That's it. That's 0, 1, 0, 0, 0, 0. you move them in forward, starting to release them again. Right, so here, that's a 2, that's a 1, so it's gonna be 21 hex. See, the reason I'm having you write out the hex for each of these segments is because when you go to simulate this decoder, right, because you'll have to simulate this decoder just like you did the MUX and also the RCA. Well, when you're looking at your timing diagram, isn't it easier just to look for a 4 0 floating hex as opposed to a 1 0 0 0 0 0 0? Right, because hopefully you all remember, because I mentioned this in my intro to Bravado video, that when you're looking at the timing diagram of Bravado, there's a wheel, like a little gear wheel. If you click on that, you can have the outputs displayed in whatever base you want. You have it displayed in binary, base 10, and also hexadecimal. So here you might want to choose hexadecimal, right? Because it'll be a lot faster to check the hex values than to check the bit values if you have binary. Okay. So do you think you could fill out the rest of this table? Okay, it all goes back to this, that in order to light a segment, you need a 0. And if you want the segment off, you need a 1. So we're just looking, you don't want a small case D. So a small case D, we want these segments to light. So those have to have 0s. And then the A and the F that we don't want to light, those would need 1s. And I'm just writing them out following this G, F, E, D, C, B, A. Okay.
One back to the lab 3 on the marks right there for the 1 value. So the 4 bits 111. Should it be 1100? Yeah, right.
Bring that question up in a little bit. Well, I'm going to explain this stuff. You're not quite there yet. Was there another question over here? I thought I saw a hand up. So, yeah, exactly. Yeah, but everybody here, it's important. Can you see that capital B is going to be a problem too, right? What's capital B going to look like? Hey, so yeah, you're going to need a smaller case B also.
So it's 6 inch have a little hack too.
Say that again.
The 6 should have a little hack on the top, like I said.
Oh, right. Yeah, the 6 would have a hat. Yeah, yeah. Otherwise, it looked like a 6 there. That's a good point. Yeah. So, do you think you can fill out the rest of this table? Now, this brings up why I changed it from BCD to X. BCD, how many rows would you have in this truth table? Have 16, you have. How many digits are there? How many characters in the decimal? 10, right? 0 to 9. See, if you're doing BCD, the 7th segment, you would just go up to 9. So the only reason I changed it to X is just to make it a little bit more interesting. Right? You got a few more rows, plus we can talk about the capital B looking like an A. But you see, that's why BCD is popular, because most of the time you want to display things in base 10. So encoders that display in base 10, they have BCD coming in because BCD just has a subset of binary from 0 to 9, which is all you need for base 10. You see, that's the reason behind BCD. Okay. All right. So like I said, filling out the rest of this table, that's the activity that you do at your table and just passing one here. All right, but we've got more to go here. I want to give you the code, or most of the code, or some of it, to do the decoder. And then I want to talk about how this diagram works. And also want to mention that this case is still a problem. And then also talk about the constraint. So it's really forward and things, so keep track in case I get but any questions before we start talking about the system learning code and where to model this decoder? Okay, everybody's good? Okay, so when you go to model your decoder, you're given a name, always do for module type all the seg. And then you're gonna declare your inputs and outputs. Now, just like with the if statement that we talked about last time, to model the MUX. Remember I said that there was something you had to do when you declared an output that was within an always cone. You remember what that thing was that you have to add? Logic, right? Same thing here, because you're gonna see that we're gonna model this decoder with a case statement. And we can if statement for the MUX. You're gonna use a case statement for the decoder. And whether it's an if statement or a case statement, they both have to go within an always cone. And what did cone, C-O-M-E, what does that stand for? Right, combinational. Okay, right. Because a MUX as well as a decoder, they're combinational logic circuits. And what do we mean by that? Combinational logic circuits do not have what? What don't combinational logic circuits have?
They don't need a clock cycle, but it's like it's.
Well, they don't need a clock, that's true. And you don't need a clock because they don't have this other thing. Okay, latch, which is a part of memory. There we go. Right, exactly. Combinational logic circuits do not have memory. Okay, and you're going to learn in a few weeks that the main component or a component, I guess it is the main component of memory is this thing called a latch. Okay, and when you don't have memory, you don't need a clock. Okay, and again, we'll talk about what a clock is. Okay, but the key point here, because you're going to have an output or output or not just output one within a always common, you're going to have to put the logic between the output where you take output and where you declare the input. So or the where you declare the output. So you're going to see in a moment here that the seg output is the one that goes within the case statement. You'll have to put output and logic. And then 6 to 0 stay. Okay. So after you declare your input outputs, then comes the always comment. So it's always underscore AMD on my on your here. And then you begin. Here again, I'm going from notes that were from memory, so the syntax of writing is not guaranteed. But I think that in one part of it. Okay, but the next thing is your case statement. So you type case, and then within the parentheses, it's case and then parentheses, and whatever you put in the parentheses, that's called a sensitivity. So what's meant by that is whatever you put inside these parentheses, when that changes, that's when the case gets evaluated. So you want the case to be evaluated every time the data on this input changes. So whatever you call this input of the decoder, that's what's going to go within the parentheses. See, I call this input X. Okay, but if you call it something different, then whatever you call it goes within the parentheses. Okay. Now, you're going to make a list of all the possible values of X, and then for each possible value of X, we're going to put what we want the output say to equal. So the way you do that, we're going to start with 0. So if it's a 0, we want to make say equal to the inputs right here. Okay, so you would write 7, pick mark B, and then 0, 0. Make the 1. When you write a 1, you just want B and C to write. You want this. Sometimes people have B and C is correct. Just think about if you have a 3, right? It's going to be like this. So you want the 1 over here. You guys have a question? There. You have a question, this, or give me some, okay. Yeah, just wanna make sure. So, you're gonna have to do that for all. You're think about it, right? So this is gonna go all the way to 15. I'm pretty sure. I'm pretty sure that. All of these, in basically, you don't have to actually not right. That may pull up night when it's like pretty sure that works. Yeah. But then after you're done with this, it tells you how to do it. And that's the default. After the yeah, the default. The default, you can say that whatever you want. Okay, a lot of times people will leave the default or only the middle segment blanks. And the purpose of the default is that if by some chance somehow the code didn't get any of these options, this is what the default is. So the default is like a safety net where if you don't have a default and something happens where it doesn't get any of these options in the case, well, you can get a situation where your code is just like an infinite kind of thing. Yeah. If you don't have a default, don't. Be glad. Okay, I mentioned last class that in an if statement, if you don't have an else, it creates a latch. Or in a case statement, if you don't have a default, that creates a latch. And again, a latch is like the main feature of memory. Okay, and because this is a combinational circuit, we don't want any memory. Okay, that's just adding additional circuitry that's not really doing anything, and you know, and sometimes can make your circuit not work. Okay, so you end for the last line is the default, and you have to end the case. You just write end case. Then you need an end to go with it again for the always on, and then you got to end the mod. Now let's talk about RC. We all know how the RC works. So RC is going to have to what the binary number that's going to give us a result. Carry out. Carry out you get one. So, right. If our addition is greater than 15, that's when the carry out becomes a 1, right? From 0 to 15, our carry out is 0. It's not going to reach a result of 16 or more, but the carry out becomes a 1. So let's see what's going on when the carry out is a 0. And meaning that our result is 15 or less. Well, the carry out of the RC is connected to the select of this mux. So that's going to make the select equal to 0. And you all know how muxes work, right? So when the select is at 0, what's going to be at the output of this mux? Which input is going to choose? Yeah, it's going to choose whatever is on the 0 input, which we're going to make equal to the binary 1, 1, 0. So when the select is 0, we're going to have 1, 1, 1, 0, which is going to be our AN. And remember that AN it's funny. The reason there's 4 bits is because we have 4 displays. So the 0 of AN, that goes to the furthest to the right display on your baseboard, and this particular at the bottom. Okay. So when 110 gets outputted at AN, only the furthest to the right display will light. The other 3 7-segment displays will be off. Instead, it keeps a 0 on AN to light up the display. If you have a 1 for AN, the display is going to be shut off. Okay, and what's going to determine which number, which character is shown on that AN display, AN 0 display, are the setting capitals that determine which is light up on the display that's turned on. Okay, so does that make sense? All right, so now carry on to 1, looking at a result more than 15, right? You get the output of the next one. Right, we're just going to put the data that's connected to the 1 input, the output. And if I have all the 1s going to my displays, what's going to happen? They're going to be all up. So any result greater than 15 will not be displayed because all the 7 segments will be turned on.
So why don't we just turn on when we get the 1 as criteria? We could just do 1100. So to turn on 2 LEDs, and we always have the like the second digit LED displaying 1.
So it's a very big question, and it goes to how these 7 segment displays are connected. They're all connected in what's called parallel. So unless you use something called time multiplexing, which is something I will talk a little bit about in a few weeks. If you have all the displays turned on, like if you had like all 4 displays, they're going to show the same number.
So because the what's called the segment A for that, so it'll apply to all of the.
Right, yeah, there's like 4 of these that are identical and they're all connected together.
Okay.
I don't know if any of you have heard of time multiplexing, but it's a way where you can minimize hardware. But you have to do something, you have to use a certain technique where you're basically, lighting up one display, then the next display, next display, next display, but you do it at such a rate that our eyes can't detect it. Okay, so we have a module that Dr. Mealy designed that does time multiplexing, and in a few weeks, we're going to let you use it to show multi-digit numbers on 7-segment displays. Because for you to create a time multiplexer, you're not at that point. It's beyond the scope of the course like this. Even in 233, some students I think after that class could probably do a time multiplexer, but it would still be quite a challenge. It's not a trivial circuit. Okay, so let's see. So any questions on how this works? Everything's good. All right, so let's see. One other thing about this diagram, and I mentioned this last week. When you design your LUTs, don't even think about this data that's connected to it. You're just going to, from one select bit, maybe the output equal to 1 input, the other select bit, make the output equal to whatever you call the other input. Where you take care of this binary data that connects to the MUX is in the overall structural model. So when you connect up these lower level blocks in your structural model, the RCA, right, you connect the adders up, you're going to have another file like that. Well, that's where you make this connection. Okay, because what you'll do in the structural model is you'll just put .0 in parentheses, or you can mark D1110, and that will connect this input to that data. Okay, so just like you connect like inputs together and output to inputs and so on, you can connect inputs to data. Okay, in that structural model. Okay, let's talk about the test cases. The test cases, just like for all the labs, are on Canvas. thing while we're waiting for the projector to come on is on the back side of a handout. On the back side of the handout that has the information on some things to play, it shows you what the constraints needs to look like. But some things just don't see the whole in the constraint, but just put it sitting display. So you can see you have to down the board. So you can see like seg 0, seg 1, seg 2, and so on. And then also same thing with the 4 bits for and if you get to the part where you do constraints, you just have all of this for the display. Main thing I wanted to point out is, again, this is on canvas, so make sure, for the rest of the quarter, make sure to look at what the test cases are in the lab. So you can see here, lab 3 test cases, you want to use the same 10 test cases that you use the lab 2 because you want to make sure that your RCA is still working. Okay, just because it worked last week doesn't mean it's working this week. So you got to make sure it's still working. So do the same 10 test cases as lab 2. And then you have to add additional test cases to make sure that the coder is showing all the characters, right? 0 through F. Now, there could be some overlap, because of course the 10 test cases are going to be shown. What I would recommend, just so you don't miss anything, it's better to be redundant than this one. And if it's this one, that means the design's not working 100%. It means all those points. So I would do the 10 like you did last week, and then I would just do 16 more and show 0 through F. Also, you want to make sure that if the result is greater than 15, that the display is blank. Okay, and there's a couple of test cases for the RCA where that should happen. So I think you add 8 plus 8, which clearly is more than 15, and then also like 15 plus 15. Those test cases, you do the overall, they should blank the displays for the display. Okay, so I think I covered everything that I wanted to talk about. Do you have any questions before you get started with the activity? And then after your questions for the test space. Okay. Yeah, but I guess I actually learned this from Dr. Plummer. He uses it in his class. I think it's a really good example. Where he talks about where default would come in a situation like, say, your design is on a satellite or something, and it gets hit by solar flares, and the solar flares cause bits to change that you didn't intend to change. That might take you to a default state, something like that. But yeah, it's hard, if not, I think, possible to simulate the defaults. Yeah, so that's a great question. But yeah, you can't really test it. But I do now. For the labs, I don't require that you submit code, but for the final project, I do. So that is something I look for actually when I grade the final projects, is I make sure people put, false code. Now, unless you're trying to create memory, because again, you're going to see in a couple of weeks that if you're trying to create memory, you wouldn't even fall out of it, so you wouldn't even outside of the case. Okay, any other questions? The time you have to work, like I said, work on the activity. Again, if you're leaving for a while, make sure your group finishes and passes on the activity before you leave.